Hello student, myself is Dr. Khilare, Assistant Professor of Statistics, Rao Bahadur Narayan Rao Borawaki College, Srirampur. In this video lecture, I am going to explain the recurrence relation for probabilities of Poisson distribution and limiting case of Poisson distribution. Now first we see the recurrence relation for probabilities of Poisson distribution. Okay. The relation between probability of x equal to small x and probability of x equal to x plus 1 is called as the recurrence relation. Relation between probabilities of x equal to x and probability of x equal to x plus 1 is called as the recurrence relation. If x follows Poisson distribution, if x follows Poisson distribution with parameter m, then its probability mass function is given by, then its PMF probability mass function is given by probability of x equal to small x, which is equal to e raised to minus m raised to x upon x factorial. Here x takes values 0, 1, 2, 3, so on. 0 otherwise, here parameter m is greater than 0, which is constant, and probability of x equal to x plus 1, which is equal to e raised to minus m raised to x plus 1 divided by x plus 1 factorial. Here also x takes values 0, 1, 2, 3, dash 0 otherwise. Okay, now we take ratio. Of probability of x equal to x plus 1 divided by probability of x equal to small x, which is equal to e raised to minus m raised to x plus 1, this divided by x plus 1 factorial, this whole divided by e raised to minus m raised to x, and this divided by x factorial. Okay, now e raised to minus m gets cancelled. Again m raised to x gets cancelled. Then the probability of x equal to x plus 1 divided by probability of x equal to small x, which is equal to this x factorial into this m upon x plus 1 factorial. Okay, now we convert x plus 1 factorial into x factorial, which is equal to x factorial into m divided by x plus 1 into x factorial. Now x factorial gets cancelled, and which is equal to m upon x plus 1 only. Therefore, probability of x equal to x plus 1, which is equal to m upon x plus 1 into probability of x equal to small x. Here x takes values 0, 1, 2, 3, dash 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 dash. This is the recurrence relation for probabilities of Poisson distribution. This m is the parameter which is constant. If m is known or it is estimated by using the given data, then the probability of x equal to 0, which is equal to e raised to minus m. Okay, if m is known, in that case we will have a probability of x equal to 0. Then this probability is called as the initial probability. If probability of x equal to 0 is known, then by using this recurrence relation we can calculate the probability of x equal to 0. Okay, this is the probability of x equal to 0. Now we have to compute the probability of x equal to 1. Now put here x equal to 0 in this recurrence relation. If x equal to 0, then probability of x equal to 1, which is equal to m upon x equal to 0, means here is only 1 into probability of x equal to 0. Okay, now probability of x equal to 0 is equal to e raised to minus m, which is equal to m into e raised to minus m, which is the probability of x equal to 1. Now put x equal to 1 in the above recurrence relation, then we have probability of x equal to 2, which is equal to m upon 2 into probability of x equal to 1. Now we know that probability of x equal to 1 is equal to m into e raised to m, which is equal to m upon 2 into this probability is, that is m square into e raised to minus 1. In similar way we can calculate the probability of x equal to 3, x equal to 4 and so on. Okay, in this way we can compute the probabilities of Poisson distribution using this relation if probability of x equal to 0 is known. Okay, this is the recurrence relation for probabilities of Poisson distribution. Now we see one example on this. Example is for a Poisson distribution for a Poisson distribution, probability of x equal to 1, which is equal to 0.03, and probability of x equal to 2, which is equal to 0.2. Then compute probability of x equal to 0. Okay, now solution of this problem is given probability of x equal to 1 is equal to 0.03 and probability of x equal to 2 is equal to 0.2. Now by using recurrence relation, first we find out the value of the parameter m. Okay, we are given that this one now, which is equal to probability of x equal to 2, which is equal to, in this relation we put x equal to 1, then we will have a relation probability of x equal to 2, which is equal to m upon 2 into probability of x equal to 1. Okay, that is probability of x equal to 2 is equal to m upon 2 into probability of x equal to 1. This implies that probability of x equal to 2, which is equal to 0.2. 0.2 is equal to m upon 2 into probability of x equal to 1, that is 0.03. Okay, now again, which is equal to, this implies that 0.4 is equal to m into 0.03. Again, this implies that m is equal to 0.4 upon 0.03, which is equal to 40 upon 3. This is the value of parameter m. M is equal to 40 upon 3. Now we can find the probability of x equal to 0. We know that probability of x equal to 0 is equal to e raised to minus m. Okay, now put value of m here, that is e raised to minus 40 upon 3. This is the required probability, that is probability of x equal to 0. That is, by using recurrence relation we can compute the probabilities. Okay, now we see the limiting form of Poisson distribution. Okay, Poisson distribution as a Poisson distribution as a limiting form of binomial distribution. Limiting form of binomial distribution. Okay, if x follows binomial distribution with parameters n and p, then its PMF is, then probability of x equal to small x, which is equal to ncx into p raised to x into q raised to n minus x. Here x takes values 0, 1, 2 up to n and 0 otherwise. This is the probability mass function of binomial distribution. Okay, if parameter n is large, that is n tends to infinity. N tends to infinity means the value of n is large possible, and this parameter p tends to 0, that is value of p is very small. In that case, to compute the probabilities using binomial distribution is very difficult. For example, suppose n is equal to 50. N is equal to 50 and p is equal to 0.01. Okay, then the probability of x equal to 10, probability of x equal to 10 is equal to 50c10 into 0.01 raised to 10 into 1 minus 0.01 raised to 50 minus 10. Okay, then using binomial distribution to calculate this probability, it is very difficult. Okay, now to overcome these difficulties, the French mathematician Poisson has used the limiting case, that is binomial distribution. If n tends to infinity and p tends to 0, in that case the binomial distribution tends to the Poisson distribution. Okay, now we see this result and prove this one. Statement: if suppose x follows binomial distribution with parameters n and p. Okay, then if n tends to infinity and p tends to 0, okay, then this binomial distribution, tends to the Poisson distribution, with parameter m is equal to n into p. M is the parameter of the Poisson distribution. Okay, now we prove this result. Proof is, see, if x follows binomial distribution with parameters n and p, then its probability mass function is given by probability of x equal to small x, which is equal to ncx into p raised to x into q raised to n minus x. Here x takes values 0, 1, 2 up to n and 0 otherwise. Okay, this is the probability mass function of binomial distribution with parameters n and p. Okay, now probability of x equal to small x, which is equal to n factorial upon x factorial into in bracket n minus x factorial into p raised to x into q raised to n minus x. Now to cancel the n minus x factorial, the n factorial can be converted into n minus x factorial as follows, which is equal to n into in bracket n minus 1 into in second bracket n minus 2 dash 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 into in bracket n minus x plus 1 into in bracket n minus x factorial, this whole divided by x factorial into n minus x factorial into this p raised to x into q raised to n minus x. Okay. Now this n minus x factorial, n minus x factorial gets cancelled, which is equal to 1 upon x factorial into n minus 1 into n minus 2 into dash 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 into n minus x plus 1 into, now p is equal to what? We know that m is equal to n into p, then p is equal to m by n. Here is m upon n raised to x into in bracket 1 minus m by n raised to n minus x. Q is equal to 1 minus p. Okay, that is p is equal to m by n. Now which is equal to 1 upon x factorial. From this each term we take n common, small n common, then we have this n into n into n into dash 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 n into in bracket 1 minus 1 upon n into in second bracket 1 minus 2 upon n dash 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 into in bracket 1 minus x plus 1 upon n into this m raised to x upon this n raised to x into in bracket 1 minus m by n bracket raised to n minus x. Okay, now the product of this n, that is n into n into n into n, this is the x terms. These are the x terms. Then the x time product of n, x time product of n is equal to n raised to x, which is equal to 1 upon x factorial into, this is the n raised to x into in bracket 1 minus 1 upon n into in second bracket 1 minus 2 upon n dash 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 in bracket 1 minus x plus 1 upon n bracket complete. Okay, now this m raised to x upon n raised to x into in bracket 1 minus m upon n bracket raised to n minus x. Now this n raised to x gets cancelled. This is the probability of x equal to small x. Now we take limit as n tends to infinity on both sides of this equation. That is, limit n tends to infinity of probability of x equal to small x, which is equal to limit n tends to infinity of 1 upon x factorial into in bracket 1 minus 1 upon n into in second bracket 1 minus 2 upon n dash 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 into in bracket 1 minus x plus 1 divided by n into m raised to x into in bracket 1 minus m upon n bracket raised to n minus x. Okay, then this is equal to, now see, the limit n tends to infinity of 1 minus m upon n raised to n minus x, which is equal to limit n tends to infinity of 1 minus m upon n bracket raised to n divided by in bracket 1 minus m upon n bracket raised to x. This limit is equal to e raised to minus m. Okay, the limit as n tends to infinity of 1 minus m by n bracket raised to n minus x, which is equal to e raised to minus m, and the limit of 1 minus 1 upon n, which is equal to 1 upon n as n tends to infinity, which is equal to 0. This term is equal to 0, again this term is equal to 0. There remains only 1 1 1 1. Okay, now the probability of x equal to small x, which is equal to 1 upon x factorial into 1 into 1 into 1 dash 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 1 into m raised to x into e raised to minus m, and which is equal to e raised to minus m raised to x upon x factorial. Here x takes values 0 1 2 so on. This is the probability mass function of Poisson distribution with parameter m. Okay, this is the limiting case of Poisson distribution, or Poisson distribution as a limiting form of a binomial distribution. Means under certain conditions, that is as n tends to infinity and p tends to 0, in that case the binomial distribution tends to the Poisson distribution, and we proved this one now here. Okay, thank you.